Good morning, sir. My name is Kevinella. My roll number 259558626. I am from CSE Department of AML D section. The course is the Database Management System. My topic title is Artificial Intelligence Enabling Cellular Networks, a critical path to beyond 5G and 6G. We can go through this. First, that evolution of cellular networks from 1G to 6G. First one, the 1G. The 1G introduced analog voice communication in the 1980s, limited to the basic telephony without data support. And coming to the next, the 2G enabled digital voice and SMS with GSM standards that introducing TDMA and CDMA modulation techniques. And next, third, the 3G. The 3G brought mobile internet via WCDMA and achieving peak data rates up to 2 Mbps using adaptive modulation and coding. And that the 4G LTE. The 4G LTE adopted OFDMA and MIMO that supporting up to 1 Gbps through scalable bandwidth and advanced channel coding, that is the turbo codes. And the next one is the 5G. The 5G NR utilizes mmWave, massive MIMO, and network slicing, while 6G targets gigahertz frequencies, AI native architectures, and sub-ms latency. This is the evolution of cellular networks from the starting from 1G to 6G, and these are the introduction for the cellular networks. And the next is AI in wireless communication core paradigms. The machine learning models such as CNNs and RNNs are used for challenging estimation and signal detection in fading environments. And the next one is reinforcement learning. The reinforcement learning optimizes resource allocation by modeling base stations as agents interacting with dynamic network states. And the next one is federated learning enables collaborative model training across distributed base stations without sharing raw user data, preserving privacy. And the next one is deep neural networks that they can approximately complex nonlinear functions in physical layer processing, such as symbol detection in higher order QAM. And the last one is graph neural networks. The GNS models or network topology for intelligent handover and interface management in heterogeneous networks. These are the core paradigms of the wireless communication AI that can use it for estimation and signal detection in fading environments, and they can access agents and they can interact with dynamic network states, and they can collaborate model training across distributed base stations, and the deep neural networks can complex nonlinear functions, and they can detect in higher order QAMs, and these can be used for intelligent handover of the interface management through these heterogeneous networks. And next, AI-driven radio resource management. AI optimizes power allocation using convex optimization frameworks, enhancing DRL, minimizing interference under QoS constraints. And the next, the dynamic spectrum access is enabled via Q-learning, where agents learn optimal frequency band selection in real-time cognitive radio environments. And the next one is user scheduling in OFDMA systems is improved using supervised learning to predict channel quality indicators, that CQI, from historical CSI data. And the next one is the load balancing across cells is achieved through multi-agent reinforcement learning, that where each G node B learns to offload users based on traffic patterns and SINR. The optimization objective minimizes total transmit power subject to rate constraints that are minimum of sigma P of I that estimates or I greater than or minimum, that can be solved via Lagrangian relaxation with neural approximators. These are the AI-driven radio resource management that can optimizes power allocations, and they can have the dynamic spectrum across that can access is enabled via Q-learning, and they can provide supervised learning to predict channel quality indicators, and they can load balancing across cells, and they can optimize the objectives and minimizes the total transmit power that has the subject to rate the constraints. And next, the intelligent beam forming and massive MIMO optimization. The hybrid beam forming in wave systems uses DNNs to predict optimal analysis pre-records from limited CSI feedbacks. And the next, massive MIMO channel estimation is enhanced via compressed sensing and sparse recovery algorithms trained on spatial correlation patterns. The zero forcing and MMSE pre-coding weights are dynamically adjusted using online learning to adapt to user mobility and blockage. And the achievable rate for user K is given by RK, this formula, and the where K is the beam force forming vector. We can go through the formula that achievable rate for user K, and that AI models reduce pilot overhead by 40 to 60% through predictive channel extrapolation using LSTM networks on time series CSA data. This is the intelligent beam forcing and massive MIMO optimization, and the network slicing and service orchestration with AI. Now that network slicing partitions physical infrastructure into virtual networks tailored EMBB, URLLC, and MMTC use cases. The AI-driven slice admission control uses classification models, example SVM, random forest algorithms, to predict resource demand and prevent over-provisioning. The dynamic slice reconfiguration is performed via RL, where the agent adjusts the bandwidth and latency budgets based on real-time KPIs. The slice isolation constraint ensures the summation of RS less than our total, where RS is the allocated rate for slice S, and the enforced via neural policy networks. And next, the federated learning across edge clouds enables collaborative slice optimization while maintaining data sovereignty and low latency response. And next one is the AI for predictive mobility and handover management. The first one is the user trajectory prediction employs LSTM or transformer models on GPS and data to forecast cell transition with greater than 90% accuracy. And next, it can hand over decision algorithms, integrate predicted SINR, load, and velocity to minimize ping pong effects and all call drops. The handover trigger condition is modeled as a Markov decision process with states representing cell associations and rewarded based on QoS. The reinforcement learning policies reduce handover failure rate by 35% compared to traditional A3 by A5 event based schemes in high mobility scenarios. And the mobility robustness optimization that MRO uses for clustering algorithms to identify problematic handover zones and adjust hysteresis margins dynamically. And these are the AI predictive mobility and handover management system. And next, AI enhanced channel estimation and equalization. The first one is the deep learning based channel estimators, examples channel 8, outperform the LS MMSE methods in low SNR and high Doppler conditions. Next, this received signal model is Y equal to Hx plus N, where H is estimated via CNNs trained on simulated or measured channel impulse responses. And next, the autoencoders are used for end-to-end communication system designed jointly, optimizing modulation, coding, and equalization. And next, the neural equalizers replace traditions LMS or RLS filters, reducing BR by 2 to 3 orders of magnitude in doubly selective channels. And next, the transfer learning enables rapid adaptation of channel models across different deployment environments like urban, rural, indoor, etc. And next, security and anomaly detection in AI native networks. That AI models detects jamming and spoofing attacks using unsupervised learning. That like layer features like RSSI and phase distortion. And the autoencoders to identify anomalies in network traffic by reconstructing normal behavior and flagging high reconstruction error events. And next, the adversarial training improves robustness of DNN-based detectors against evasion attacks using gradient-based perturbation methods. The detection threshold is set via Newman-Pearson lemma to maximize detection probability under a fixed false alarm rate constraint. And next, this is the edge intelligence and the distributed AI for low latency processing. That mobile edge computing hosts AI interference models close to users and the latency to less than 10 ms for real-time applications. And this can has the model partitioning splits and the computation offloading decision minimizes total. And the edge AI enables real-time beam prediction and interference coordination in ultra dense and this can distributed training via gossip algorithm or parameter server cells AI model update across geographically. And this is the AI for energy efficiency and green networking. That the sleep mode optimization uses reinforcement learning to dynamically deactivate and the predictive energy harvesting scheduling is renewable power cells uses weather forecast and LSTM based load predictions and the AI-driven cell zooming adjusts coverage area based on traffic density, reducing interference and power usage during off-peak hours. And these are the challenges and research directions in AI that to native 6G. It can explainability of AI decisions remains critical for trust and regulatory complications, safety sensitive applications like autonomous driving. This can convergence of AI and communication theory demands new matrices behind accuracy, such as latency, robustness, and sample efficiency. The standardization efforts are example 3GPP releases 18 plus or integrating AML into RAN and core network protocols with defined interfaces. This is a case study of AI-enabled 5G network deployment at IRE that the campus-wide 5G test bed was deployed using Open RAN architecture with the powered RAC and the RL optimized handover parameters, reducing dropped calls by 42% during peak academic year hours. And the digital twin simulations predicted coverage gaps, guiding antenna placement and reducing dead zones by 60% and the energy savings of 35% were achieved through AI-driven sleep scheduling and traffic aware resource allocation. Thank you.